Welcome to this explainer. Today we're looking past all that fire and smoke to uncover the actual physics, the engineering, and the core metrics that make spaceflight, well, possible. If you've ever watched a rocket launch, felt that crazy rumble right in your chest, and wondered what on earth is actually happening inside those massive machines, you are in exactly the right place. Let's just dive right into this visceral display of raw power. What we are looking at is the Titan III launch vehicle shortly after liftoff. Those two solid propellant strap-on motors on the sides, they are generating an absolutely awe-inspiring 2.4 million pounds of thrust. Think about that. We're going to break down exactly how that staggering amount of force is generated, and crucially, how it's controlled. To demystify all this complex machinery, our agenda today is straightforward. 1. The basics of thrust. 2. The rocket engine zoo. 3. Real-world applications. And 4. Grading rocket performance. Section 1. The basics of thrust, stripping away the magic. So, the most crucial thing to wrap our heads around is that thrust is absolutely not magic. It's not pushing off the ground, and no, it isn't pushing against the surrounding air either. It is simply Newtonian mechanics in action, utilizing the kinetic energy of expelled mass. Basically, you're ejecting propellant out the back at an incredibly high velocity, and that reaction force is what pushes the vehicle forward. Now, this might sound like abstract physics, but it's actually something you've probably felt in your everyday life. Thrust is the exact same reaction you feel when a recoiling gun pushes back against your shoulder after firing a heavy bullet. Or think of a garden hose violently kicking backward in your hands when you suddenly crank up that water pressure. A rocket is really just taking that exact same everyday concept and scaling it up to an astronomical level. But to create that massive of a reaction, you need extreme energy. And I mean extreme. Combustion inside a chemical rocket can reach up to 7,400 degrees Fahrenheit. To put that into perspective for a second, that is roughly twice the melting point of steel. Because these gases are just unfathomably hot, rocket engineers absolutely have to design advanced cooling systems and use heavy insulation on all the internal surfaces. Otherwise, the engine would literally melt itself into a puddle during flight. All of this immense heat rapidly expands the gases inside the combustion chamber, violently accelerating them out of a highly specialized nozzle. We're talking about gases being ejected at staggering exhaust velocities of up to 14,100 feet per second. It is exactly this high-velocity ejection of mass, literally thousands of pounds of it every single second, that imparts the necessary momentum to lift a vehicle weighing millions of pounds completely off the Earth. It's just wild. Section 2. The Rocket Engine Zoo, categorizing the beasts of propulsion. Okay, so the two dominant beasts in our metaphorical zoo here are liquid engines and solid motors. Liquid engines are incredibly complex machines. They use these intricate turbopumps to feed liquid oxidizers and fuels directly into a thrust chamber. And the beauty of this is it gives engineers the ability to throttle the thrust or even shut the engine completely down and restart it in space. Solid motors, on the flip side, are remarkably simple. They have practically zero moving parts. But there is a pretty huge catch. Once you ignite a solid motor, it burns relentlessly until it is entirely empty. You cannot just flip a switch and turn it off. Taking this from theory to a literal blueprint, let's look at the internal cavity of a solid motor. The solid propellant, which is called the grain, is bonded directly to the outer casing. When it's ignited, it burns smoothly along those exposed internal surfaces. The hot gas flows straight out through that supersonic nozzle at the back. What this means is that the entire pressure vessel itself is actually acting as the combustion chamber. But beyond those standard chemical options, engineers have cooked up a fascinating array of alternatives. For example, we have hybrid rockets, which mix a liquid oxidizer with a solid fuel. Then there are cold gas thrusters, which essentially just vent stored, high-pressure nitrogen for tiny, precise attitude adjustments. We even have these futuristic ion thrusters, which only work in a vacuum, by the way, that shoot electrically charged xenon gas at exceptionally high speeds. Oh, and get this. There are conceptual solar thermal rockets that use giant parabolic mirrors to focus sunlight just to heat up liquid hydrogen. How cool is that? Section 3. Real-world rocket applications. Escaping gravity.
A perfect example of mixing these different engine types for one complex mission is the Space Shuttle. You might just think of it as one single vehicle, right? But it actually utilized an incredible 67 separate rocket systems. It used 2 massive solid rocket boosters just to muscle its way off the launch pad, 3 liquid hydrogen-fueled main engines to actually achieve orbit, and then 44 tiny pulsing reaction control thrusters to carefully manage its attitude while floating up in space. Throw in 16 separation motors, and it is an absolute masterpiece of using the exact right tool for the right job. Now, to actually reach space efficiently, virtually all launch vehicles rely on this brilliant concept called staging. It's a sequential process. First, you ignite the massive lower booster to fight your way through the thickest part of the Earth's atmosphere. But once that lower stage burns through all its propellant, those empty tanks, they just become useless dead mass. By discarding that heavy dead weight mid-flight, the upper stages have so much less mass to push. This allows the final payload to efficiently accelerate to the extreme terminal velocities needed to actually stay in orbit. Section 4. Grading rocket performance, the math of success. So the most vital metric you really need to know here is called specific impulse. You can effectively think of this as the miles per gallon rating for a rocket engine. It measures exactly how much thrust force you get per unit of propellant weight flowing through the engine each second. The higher that specific impulse number is, the more efficient the engine is, and that means you can carry much heavier payloads or travel way farther out into space, all on the exact same amount of fuel. Comparing these numbers, you might actually be a little surprised. Notice how turbojets and ramjets have a specific impulse well over 1,000 seconds, while our trusty chemical rocket is sitting all the way down at 270. So why do rockets seem so inefficient? Well, it's because air-breathing duct engines get to pull their massive oxidizer weight directly from the atmosphere as they fly. The rocket, on the other hand, has to carry every single ounce of its own oxygen in incredibly heavy tanks. But the trade-off is absolute freedom. Only the chemical rocket has the complete independence to operate unconstrained by altitude, thriving in the dead vacuum of space where a turbojet could literally never survive. Another critical grade to look at is the mass ratio. This measures the dramatic difference in weight between a fully fueled vehicle sitting heavily on the launch pad and the relatively lightweight, empty shell that finally makes it into orbit. A highly optimized rocket has to carry an immense, almost unbelievable amount of propellant just to lift its own structural weight. Just think about what this propellant mass fraction actually means for a highly efficient system. An astonishing 91% of the total vehicle weight is purely explosive propellant. That leaves just 9% for the actual hardware, and that tiny 9% has to account for literally everything else. The engines, the guidance systems, the payload, and those ultra-thin tanks that somehow manage to contain all that highly pressurized, freezing cold fuel without collapsing in on themselves. We've pretty thoroughly mastered the chemical combustion that got us to the moon, squeezing every last drop of efficiency out of our liquid and solid engines. But I'm going to leave you with this thought as we wrap up this explainer. When you consider the truly vast, mind-boggling distances of deep space, what radical new leaps in physics, maybe nuclear fission or massive solar photon sails, what will we actually need to finally propel humanity to the stars?